And yeah, let's make this a nice experience as possible. I'd rather make sense than be fast. And so if I'm not making sense, please interrupt me. So this is all about test 3 content. If you missed my reviews last week for test 2, please send me a message and I'd be glad to share those videos with you. This is all about what's coming next. And so just a real quick background of what's happening. If you think about it, in test 1, what did we actually accomplish? Test 1 gives a lot of foundational stuff, but the biggest idea about that unit, test 1, I'm just kind of referring by the test number, but this unit focused primarily on what a distribution was, how to find the center, how to determine skew, all that crazy stuff. And then test 2 was all about how to find a probability based on the distribution. What test 3's fundamental aspect is going to be about is using these 2 facts to make a decision. So what we're going to do is we're going to have some kind of claim, some kind of belief. That claim may be a classical belief, or it may be a gut feeling. The name for that kind of probability escapes me, but it's the one that's not classical or relative. It's just kind of like how you feel it should be working. And what we're going to do is compare this to a relative frequency. Because one thing we learned in test 2 is a relative frequency, what we know it does is it approaches the true center. Obviously, the bigger and bigger the sample is, the more close it is to the real population center. And so what we're going to do is take this calculation that we know if we get big enough, it's a large enough sample, it should be very close to what the real center is. And we're going to compare it to the claim. And if they're so different, then what we're going to say is your claim is wrong. And we're going to be able to reject a claim. But if the claim is relatively close, then we're going to say, well, it might be true. And so what we're going to learn how to do today is simply how to compare these things to this one. Or not today, but that's the overall big arching concept of Unit 3, or Test 3. And then for the final section after Test 3, you're going to learn what happens once we know this, in fact, is accurate. What then we do then? So for now, we're just going to learn how to compare these 2 things officially so we can make decisions about whether or not our claim is true or not. And one of those methods is called a confidence interval. And today we're going to do a confidence interval about a proportion. And you may get a big hint as to what I mean by proportion. We see P and Q here. That means we're talking about a binomial situation. So we're going to learn about confidence intervals for binomials, essentially. We just call them proportions when they're in this context because what we're talking about essentially is some kind of fraction, like a proportionate amount. And so it doesn't necessarily have to be guaranteed to be binomial, but for the most part, they will be treated as such. And now one other thing I want you to notice is even though we're doing binomial, we're going to be using norm to calculate it. And so you might be wondering, well, how can we do that? Well, remember by the central limit theorem, if we have a sufficiently large sample size, then even the binomials can be treated normally. And so that's what we're going to be doing. We're going to convert these binomial situations into normals and then determine whether or not a claim is reasonable. Now that's the background, the underlining pinnings of what we're doing, but let's actually do the big hard part, what these formulas are and how we're going to use them. First and foremost, some cleanup. You know from test 2, I am not a fan of this .s version of the formula, so you're not going to see me use it. Instead, I'm going to do a very similar version, and that's going to be norm.inv, 2 parentheses, 1 plus the c, which you'll learn is the confidence level. Close your parentheses, divide 2. This calculation will give us a measurement that we're going to need called a critical value. So this z alpha over 2, that z alpha over 2 is known as a critical value. And we'll learn later on, for now we're just going to calculate it, but we'll learn later on, you'll learn in your class at least, what exactly is a critical value. But to get the critical value, it will just be this calculation. It's just talking about z-scores given 0, given 1. So it's very similar to this formula. I just do the full version of the 0, 1. I don't waste my time learning another formula for the test or for the unit. So that will give us the z calculation right here in the front. And then the rest, of course, we can just see as a square root pq over n. So what we're going to do in a little bit is build a calculator. And the point of that is once we have the calculator up and running, it's just a matter of copying and pasting the right calculator into the question and plugging in your numbers. And so we'll utilize that. And so what we're going to notice is we're going to build a calculator that will give us this E. This E out front is not standard error. It's known as margin of error, something slightly different. And so the calculator we're going to create is going to be a way of calculating the margin of error really, really fast. Margin of error, for those who are so gosh darn curious, is a more precise way of calculating the usual range. Remember in test 1 and 2 was center minus 2 standard deviations and center plus 2 standard deviations. But this minus 2 and plus 2 is very arbitrary, and it doesn't apply too well to samples. So instead, what we're going to do is center minus the error and center plus the error as our new, more precise calculation. And so this margin of error, we just call error for short. And of course, your center is whatever is your center of measurement. In this case, it would be our P. And we often call it P hat when you're talking about a sample versus regular P. So P is proportion, P hat is sample proportion. And so we're simply going to find a level of error around our proportionate measurement, because we know that the sample measurement is similar to the mean, but it's not actually the mean. It's just close to it. And so we have this P hat plus and minus the error. And that's what we're going to calculate. It's this calculation itself that becomes the confidence interval, the lowest acceptable number up to the highest acceptable number. And then we also have a rewrite of this statement that allows us to find a sample size. And so I can also use this formula now, which is just a rewrite of the one over here on the left, to automatically generate what sample size we need given the information we have about the question. That's enough of me blabbing on. Let's actually get our Excel built and then see all this stuff in action, because when you see it in action, you tend to learn it better. So let's jump to calculators, and I'll explain how this setup is done for us. All the yellow boxes, these are our inputs. So input, input, input. All the white boxes will be formula. So formula, formula, all the way down. And so the cool thing is, once you put in your 3 inputs and you hit enter, Excel will automatically do all these calculations for us and give us everything that we need. So once you build your formula one time, you can just copy and paste what you want in there, and it will automatically fill everything up. And you'll see that. So let's actually get building our calculator. So the first measurement that we see is the Q hat measurement. We remember P and Q from test 2. Q is just not P. So it's going to equal 1 minus the P calculation, that B2 box. Standard error for binomials or proportions is this part right here in purple. Because remember, margin of error, I didn't actually mention that, margin of error by definition will always be your critical value times standard error. And we know this Z is the critical value, as I mentioned earlier, so this must be standard error for a binomial. So it's just the square root of P times Q divided by N. And so for our standard error box, it will equal the square root our P calculation times our Q calculation divided by the sample size. So B2 times B3 divided by B4. Close your parentheses, hit go. And it's okay saying divide by 0 because we don't have any numbers in here yet. But if you were to put numbers in there, you can see that it does start calculating for you. So we know it works. The confidence level, you'll learn more about what it actually means later, but for now, it's just going to be a number we're going to put in here. Then that Z is that Z alpha over 2 calculation, this norm dot inverse thing. And so it will always be equals norm dot inverse, 2 parentheses, 1 plus whatever the confidence level is, so that first box right there, a B6, close it, divide it by 2. And because it's a z-score, we have a 0 and a 1 for our mean and deviation. And that will give us our z-score. So if I'm what we would say 90% confident, I get a z-score of about 1.65 and so forth. And remember, margin of error is defined as standard error times critical value. So standard error times my z-score, which is the critical value. I now have my margin of error. And so now I'm ready for center minus the error, which in this case is your p hat minus your error. I have p hat plus your error. And that represents our first calculator. So we just throw in some random numbers, maybe 0.8 for my p hat. Sample size of, let's say, 40 people. And we'll say we're 90% confident. And see what it did. Everything generated that we're going to need. You just need these 4 calculations and it's all done for us rather instantly. So building your calculator will save you so much time on test 3 material. I'm going to erase the yellow boxes because those are our new inputs that we're going to need. And now we're going to build a minimum sample size calculator. And I just wrote that and spelled the word sample. My bad. Boom. Minimum sample size calculator. So again, all the yellow boxes are inputs. All the white boxes are formulas. So we're going to write our first Q hat formula. And so that's going to be, of course, your P hat from 1, so 1 minus P hat. That's how we find Q, right? Our z-score, we did that earlier. That is going to be equal to norm.inv, 2 parentheses, 1 plus the confidence, divide 2, given 0, given 1. And again, I'm just getting this from your lab manual. The formula is right here. And we have our norm inverse calculation and all that fun stuff. So the sample size calculation, that's going to be this calculation down here. So we can see it's going to be P times Q divided by, in parentheses, the error squared Z squared. And so it's a matter of just doing the formula. So P times Q divided by, in parentheses, the error squared divided by Z squared. So what are you just clicking on the appropriate box? We have the margin of error is your error, Z is your critical value, all that fun stuff. And let's just double check and make sure the error is on top, and we can see error squared is on top of Z squared, so we're good. And then this last step right here is we're talking about human people. And so if it says, let's put in some random numbers, 0.5, maybe a confidence interval of 90%, and then let's say an error rate of 4%, and you'll learn how to do all this and stuff. We can see it's 422.7. And so we're trying to find the minimum acceptable number. And so no matter what that number is, it always has to round up because 422 wouldn't be enough. And so even if that was 422.1, it wouldn't be enough. So no matter what, we want to tell Excel to always round up and not have to think about things. And there's actually a formula for that. So in this last box, we're going to say equals round up as one word. That tells Excel to round up no matter what. So we don't need to think about things. Open your parentheses, click on the number you want to round, and tell it for 0 decimal places. That way it will always round up to the nearest whole number. Close it and hit enter. And there it is, rounding up. So even if this was 422.1, it would still round up to 423. It's going to force it to round up no matter what. And you don't need to think about it anymore on which way to round it properly. Now, obviously, if they told you to round to the nearest whole number, you would do that. But by convention, we always round up, even if they don't tell you. So that is making our calculators. And now we're just going to use them and see how they are in practice and when we can't use them. Because there's some cases where you actually can't use them, and we'll talk about that. For those who came late, this is a test 3 boot camp for the newest tests. And so if you're looking for test 2 material, send me a message and I'll send you the videos from last week when I went over test 2 content and did a test 2 review. This is all about confidence interval proportions, which is the first section you'll learn on the test 3 section. Okay, so let's look at the first question and decide which calculator we want to use. Do we want to use a confidence interval for proportions calculator, or are we looking for the minimum sample size? I need to erase those yellow boxes so we can actually have a clean one to copy in. So we're going to look at the first question. And if you've been with me for a while, you know the first thing we should always do is start at the question and go backwards. That will tell you exactly what you need to do. So starting down here, it says construct a confidence interval. Okay, so we look at our calculators. Which one's going to build a confidence interval? Well, the one on the left, the one called a confidence interval calculator. So without even reading anything else, I already know I need this calculator. So I'm just going to copy it by Control-C or Command-C, computer you got. Go into my new spreadsheet and pick a place that I want to put it. I'm going to put it down here and just paste. And the really cool thing is, if you click on these cells, you'll see all of your formulas come with it. And so you don't need to rewrite it from scratch every single time. It will automatically come in with all of your formulas. And so once you build this one time, you can then just copy and paste it into new spreadsheets every single time, and it will automatically do all of your calculations. And so now that we're building a confidence interval, we just got to pick out the information. We need to find our p-hat. Remember, p-hat is just your proportion. It's just your fraction amount. It's just a probability amount, a relative frequency, in other words. And so it should be between 0 and 1. So we're trying to find the proportion, the fraction of internet users. And we can see it's 528 of 1774. So p-hat is 528 out of 1774. If it's not a fraction, it's not a proportion. It has to be a fraction, decimal, or percent. Okay, so I got my p-hat. That means I can go ahead and fill in the first box down here. Don't forget your equal sign. 528 over 1774. Hit enter, and it starts updating. It already calculated q-hat for me. Now we just need the total sample size, and that should be obvious. That's the 1774, the total amount, just our denominator, in other words. So 1774, and boom, we got some calculations going. We just need our confidence level, and we're done. Our confidence level, it tells you in the question. They have to tell us, or we assume it's 95%. And they're telling us, and it happens to be 95%, so we just write that in. 95%. And poof, we are done. This is the calculations that you need to do. The way you talk about your answer is you indicate the lower and upper limit. So these values down here at the bottom are the most important. So we would say that we are 95% confident the true population proportion is between my lower limit of 0.276 and my upper limit of 0.319. So what exactly am I saying by this? I'm telling you, because it's a confidence interval, that I don't know what the actual center of the internet users is. I don't actually know what percentage of internet users say that they use it almost constantly. I have no idea, but I do know with a 95% accuracy rate, essentially, that it's somewhere between 27% and 31%. So I can at least narrow it down to a very small window. And so I may not know what the proportion for all users are, but it's definitely between 27 and 32%, or 28 and 32, depending on how you round it, right? So that's at least giving me a small net where I can be highly confident where the true population proportion is. And so how do we use that? Well, now we can look at somebody's claim, part B, and we're trying to find out if their claim is consistent for what we have determined. And so in other words, they're saying that the real answer, the real population proportion, they think the proportion is 35%. But we are 95% confident, 95% sure that the answer should be between 27 and 32 roughly. So are our results consistent? Well, is 35 between these numbers? And the answer is no, right? 35 is not between, this is 0.35 in decimal form, is not between those numbers. And so it's not consistent, which means if we were doing like a study or an experiment on their work, we would say we believe their results are incorrect. We're 95% sure, which means that there's 5% of the time we are wrong, but 95% of the time I'm right. And so pretty reliable on the fact that 35 is just the wrong number to think is the right answer. So something was wrong with their study based on our information. Now, of course, this is only 95% accurate, essentially, right? So there's a 5% chance that we're actually the wrong ones. Who knows? And we'll get deeper into the course to learn more precisely how to talk about this 95%. For now, when we make these comparisons, you just need to know, is this number between those numbers? If it is, we say that it's consistent or reasonable. If it's not, it's inconsistent, aka unreasonable, as an assumption. So in this case, 35 is not between those numbers, so it's not consistent. Let's see how easy it was. We just plugged our three numbers in and poof, we got our answer down below. Read the next question. So on this one, I'm going to point out some notation for us. Remember, the whole point of a confidence interval is we're getting some center minus error and some center plus error. So we have this minus and plus idea. And so if you look carefully, that's exactly what they're showing us here, which means that this must be the center measurement. In this case, proportions, we're talking about proportions in this unit. And this must be the error, which means they already did all these calculations for you. They already determined what the error is. Because remember, our formula here, all this work is just to get the margin of error. But they already told us the error is 0.052. So this is one of those cases where the calculator won't be necessary because you already know all the numbers. We have our center measurement of 0.447. And we're going to subtract our error, 0.052. And that will give us, since it's a subtraction, that will give us the lower boundary. And then similar, if I do the 0.447 plus my error, I'll get the upper measurement. And so when they give you all the numbers, there's no reason to use the calculator. It's just, well, basic kind of calculator, but there's no reason to use those formulas that we did. And we just punch everything in. There's my lower measurement. And of course, equals 0.447 plus 0.052. And there's my upper measurement. Always check your decimals. Willing to bet there's more than just one decimal there. And look at that, there definitely is. So the lower measurement is 0.395. And the upper measurement is 0.499. And so this is just an alternate way of representing it. You can represent it in interval notation. You can use what we call margin of error notation. That's this one, margin of error notation. And that's when you just list the center plus and minus the error. And then there's one more way to represent a confidence interval, and that's by inequalities. And it always goes to smaller number is less than our center, which in this case is the proportion, which is less than the bigger number. So for confidence intervals, all three methods are legitimate ways of representing a confidence interval. It just so happens that A here is the most common way you'll see in this class. But they can technically ask you to do it by inequality or the margin of error notation. They're all equivalent. We just most commonly use the A method. And so when I saw these, you're going to generally see me use the A method unless it explicitly says to use a different method. That's all there is to it. Let's jump to the next part. So right off the bat, we can see they already did the confidence interval. They made us a confidence interval already, and we just need to interpret it. So the point estimate, that's just a fancy way of saying the center. So we need to know what the center is of these two numbers. Well, if you have two numbers and you want to find the center, that's just finding the average of the two numbers, right? So we could just simply do equals average of those two boundaries, 0.455, comma, 0.485. Same thing as adding them up and dividing by 2. And so that represents our center. That is our point estimate, and we often denote the center for proportions as a P with a little hat on it. And so that's it. That was the center of this measurement. So now I want the estimate. We want the error. We often just call E for margin of error. And remember, the lower limit, this 0.455, that would be equal to my center, my p hat, minus the error. And the 0.485 would equal p hat plus my error. And so we can use either fact to find how much the error is. In general, it's easier if you use the upper amount, because then it's just basic subtraction. So that's how I'll do it. So what do we know? We know that 0.485 equals our p hat, which is that 0.47 number, plus some error. Well, we learned a long time ago, if you're doing like an algebra problem and you have a constant plus a variable, we just need to subtract off the constant. So 0.485 minus 0.47 will be the amount of error we have. And so I can say equals 0.485 minus that p hat number. I'm actually clicking on it just in case it's not exactly 47. And I get 0.02, which is a big hint that this is probably not exactly 47. Let's add a decimal just to see. Oh, it actually was. Add a decimal here. Aha, that's what it was rounding the error number. And so that represents my lower boundary. And we can always check it. If I do p hat minus error, I should get 0.455. And if I do p hat plus error, I should get 0.485. And so if I want to check my work, I simply need to subtract my two numbers. There's my lower measurement, 455, check. And if I add my two values, I get the upper threshold. So I know it works. Those must in fact be my error and my proportion, my center point estimate. And so these are the two facts that were used to create that data. Let's keep it moving. So as always, start with the question itself so you know what formula to use. And you can see, find the point estimate. That means that we're going to find our p hat. So that means we just need to write our fraction. And we see two numbers. So it's either 160 out of 23 or 23 out of 160. Well, how do I know which one it is? Remember, p hat is just a proportion, just a probability, a fraction, a relative frequency. And so like we learned back in test 2, p hat is a probability, so it must be between 0 and 1. Well, if you were to type this into the calculator, you would see that this is greater than 1. So that's telling you that's the wrong way to do it. And so we're going to pick the other orientation, 23 out of 160. And so that's what I'm looking for. P hat must always be less than 1 and bigger than 0. It can technically equal 1 or 0, but that'd be rare. Now we want to make a confidence interval. So we're going to go to calculator. We're going to highlight our calculator confidence interval. Copy. Jump to the question we're on. Pick a place that you like to place it and hit paste. All of our formulas come with it. Maybe stretch our cells just so things fit. There we go. And now we just need to fill in these 3 yellow boxes, and then we'll have our calculations. Our p hat we already figured out. 23 out of 160. Boom. What was the total sample? That's just the denominator, right? 160. And then our confidence level. They have to tell you, or you assume 95, and they're telling us 99%. So we're 99% confident that this method is going to produce the right interval. And so we get an interval of 0.072 and 0.215. So we are 99% confident the true proportion, the true fraction of all occupational therapists who happen to know sign language is somewhere between 7 and 21%. I have no idea what the answer is, but I know it won't go past 21 and it won't be under 7, right? These are the kind of the boundaries. And so whatever the real answer is, it's somewhere between those two numbers. So I mean, I can make certain interpretations. I can say, well, I can definitely make the claim that a minority of occupational therapists know sign language, because we define minority and majority as being less than 0.5. And so both these numbers are less than 0.5, so this claim is an accurate claim. I could also claim that less than 40% of all occupational therapists know sign language, and that's a true statement. I could even get more bold and say less than 30%. So this allows us to make generalizations that even though we don't know what the actual number is, we know it's at least less than or more than blank. And that's the power behind all this. And then when you get the hypothesis testing, you'll be able to figure out how to actually test specific values. For now, we're just kind of making range claims, less than certain numbers, more than other numbers, and that kind of stuff. So starting at the A, if we read it carefully, it says determine the minimum sample size. So that means that we no longer want to use the confidence interval calculator. We finally get to use the minimum sample size calculator. So I'm just going to highlight it. I'm going to copy, jump into my question, and I'm going to paste. And all of my formulas come with it. So once you write your calculator one time, you can just paste it forever and ever into any future spreadsheet you want with all of your formulas already built. That's the power of this unit. You get to spend more time understanding what these numbers mean this time rather than rushing to do a bunch of calculations. Okay. So for part A, it says using the New York Times data, the New York Times said it was 32%. So that represents our p hat. So we now know to put 32% there, and I don't bother with decimals. I'm just going to write it exactly as they wrote it, just to be consistent. And now I need the confidence interval. They're telling you be 95% confident. Now we got to determine the error. How much can we be within? And so there's your big clue word, within. So this is telling us how much error we're willing to accept. We're willing to accept 2 percentage points of error. And so we're going to simply put 2% there. And there we have it. If we want to create a confidence interval of boundaries that are only 2% points wide, then we need to have a survey of 2,090 people. That's the real beautiful part about this. If we get 2,090 participants and find whatever measurement we're looking for, when we get that calculation, it's going to be off from the real proportion calculation from the population by just 2 percentage points. It might be 2% points too high or 2% points too low, but it will be within that threshold somewhere. That's the real power of all this stuff, is that we actually now know exactly how many people we need to go and talk to. We should go and talk to 2,090. But something interesting happens when we do this. And then we'll see why in part C. So they're essentially asking us to calculate it again, but they want us to ignore the results of the previous study. They want us to ignore that 32%. For some reason, they're saying not to trust it. So I'm just going to highlight my calculator. And I'm going to copy and paste it down underneath itself. And then what we're saying is that 32% can't be trusted. So I got rid of it. I deleted it out. And so we have to decide what to put there if we're not going to use 32%. And so this is a nice rule to note somewhere. Whenever you don't trust or disregard p hat, you must use 0.5 for p hat. So if for some reason we say that the data we have is unreliable, we fall back to 0.5. Why? Because when we don't know any information about a binary situation, remember this stuff, proportions are just binomials, either you do or don't do this stuff. If we don't know anything about the data, nothing about the existing situation, we assume it's a 50-50 shot. If I never flipped my coin in the history of flipping my coin, we're going to assume there's an equal chance of heads or tails. And so if we ever don't trust the p-hat information, we always just use 0.5 as our claim. So I can type 0.5 or you can type 50%, either way. Well, notice what happens though. It went from 2090 to 2040-01. So by changing this percent from a known value to the 50%, actually increased how many people we need to talk to. If you think about it from a practical standpoint, that should make sense. If you don't know anything about the situation, because we're not trusting that results, we're not trusting historical data, we should get more of a sample in order to be really, really sure what's going on. But there's also an algebra way of thinking about this. There's a cool fact about square numbers. If you have square numbers like 5 times 5, that will always be bigger than if you were to deviate from those values. If I were to go down 1 and up 1, I would get 24. If I were to go down 1 and up 1, I would get 21. It gets smaller and smaller the least square the numbers are. And so if I did something like 8 times 8, that's 64. And if I go down 1 and up 1, make them different, I get 63. And if I go down 1 and up 1, that would be 10 there, I get 60. And so notice that the more different the numbers are, the less the value is. And so that's the big idea. When this is 50-50, it's a bigger calculation than when it's 32 and 68. And so that's why mathematically it's always going to be a bigger number than when it's 50-50, 0.5, 0.5 for P and Q. And when it's not, it's going to be a smaller number. Now it's telling us, comparing these answers, should we do 2090 or should we do 2401? It really depends. We have to weigh 2 different factors. One, we'll have to decide on the added costs of more people. That could impact how much money it's going to cost. And so interviewing about 300 more people will cost more money than not interviewing 300 people. Versus the second idea, more accuracy. More accuracy in results. The more people you talk to, the more the information looks like the proportion. And I should say versus, VS. So I'm just going to write over here, versus. So essentially you have to weigh these 2 things. And you have to kind of decide how much of a more accurate result would I really get with 400 more people versus how much money is that going to cost me. If it's going to cost me $1,000 and I'm only going to get 1 percentage point better, I probably won't do it. But if it costs me $1 and I get 5 percentage points better, I might do it. And so these are the 2 things that you would weigh and decide. If it's cheap enough, then absolutely pick the better population if money's not an option. But in reality, you would consider these 2 things. Cost and feasibility versus how much better results you get from it. And you guys won't actually learn how to make that kind of calculation. That's just what they want to hear, that you considered what you would think about if you actually knew how to figure out how much more percentage points of accuracy you would get. But in general, if you have infinite dollars, always pick the bigger sample size because you get more accurate results. It's just in real life, we don't get infinite number of dollars, right? Fish. Okay. Reading from bottom to top, construct a confidence interval. Sweet. And so they're giving me the confidence already. That's my confidence. We're getting the proportion. That's my p-hat. And we have the total sample size. That's my n. Let's go to the calculator page. Let's highlight our proportions calculator. Let's copy. Jump to the question. Paste it somewhere that we like, maybe over here. Expand your cells as you need to. And just type in our numbers. Our p-hat was 43%. Our sample size was 1,200. Our confidence level is 90%. Poof, we're done. We are, to interpret it, we would say, we are 90% confident that the true population proportion is between these two numbers, 0.406 and 0.454. So I have no idea what the true population proportion is, but I know it's in the 40s. I know it's between 40, roughly 41, 45%. So I can definitely say that a minority of people feel this way. A minority of people think filling out their taxes is worse than going to the dentist. You know, you can make those kind of declarations now. More than 40% feel that way and less than 50% feel that way. Do I know the exact number? Absolutely not. Any number in this range is possible. It might be 41, it might be 42, it might be 43, it might be 44.9. I have no idea. I just know it's between these two numbers with a 90% confident. What this confidence level actually is telling us is that if you do this process, then 90% of the time the process works. That's what the confidence actually means. It does not mean there's a 90% chance these numbers contain the true mean. This refers to the process. And so it's telling us that 90% of the time, the process, this calculator that we built, it works 90% of the time, which means 10% of the time, even though you do all of your calculations perfectly, it didn't work. Maybe you had a bad sample. Maybe you had a bad p-hat. Who knows? But 90% of the time doing this process works. So then the question would be, well, why not do a higher percentage? Why do 90%? So let's experiment that real quick before I go on. Why aren't we just doing 99.99%? That'd be a very high confidence level. So let's actually just highlight this data. I'm going to copy and paste it twice, one to the right and then to the right again. Expand my cells. And all I want to do is see what happens if we change that confidence level. So right now we have a 90% confidence level. Let's go up to a 95%. And then let's go a little higher, maybe 99.9%. And so let's see what's happening. Currently, with a 90% confidence interval, we can see that it's between 0.406 and 0.454. So it has a range of around, if I were to subtract those two numbers, of around 0.052. So it's about a 5% distance between these numbers, 40 to 45. If I do 0.402 to 0.458, now if I subtract, it's 0.056, right? If I did the bigger number minus the smaller number. I just realized I messed this up in 48. And I'm making it all hard. I can actually just do equals that number minus this number and then expand it. There we go, 0.47, because it's apparently they're rounding a little bit. But there's the idea that this is how far apart it is. It's about 4 percentage points. And now it's about 5 to 6 percentage points. And so if I do the other one, if I subtract these two, you can see it's even getting further and further apart. Now it's about 9% of a range. And so what we're essentially doing is we're creating a larger and larger net. We're increasing the possible acceptable numbers. And so as you get higher and higher in the confidence, and that says 100%, but it's just rounding on us. If I fix that to my decimals, you'll see it's actually 99.9. But the higher and higher the confidence, the larger the interval becomes, and the less we actually know about what the real mean is. So right now, I'm confident that the mean is between 40 and 45. But if I go to 95%, now it's between almost the same numbers, but a little bit bigger. If I go way big, it gets even bigger and bigger and bigger. And so there's a trade-off. The higher the confidence you are, the more expansive, the wider the interval of possibilities are. And if we go too wide, it may be just unhelpful Me telling you that the average income of an American is between $0 and $10 million doesn't tell us anything. But me telling you that I'm 90% confident the average income of Americans between 45,000 and 55,000 tells us something, because it's a small net. So you balance out how much confidence you want to how big of an interval it's going to be. And that's the idea of what's happening here. So the more confident you are, the greater the interval will become. Because to be more confident, you need more of a range. The more range you got, the more confident, the more reliable you can say the real answers between these two numbers. That's the idea of what's going on, at least. You'll never have to pick the confidence level. They're always going to give it to you for this class. That's the good news about all this. I just want you to understand what it means to say you're 99% confident. You're saying that this process works 99% of the time. Okay. Construct a confidence interval. We go to calculators. We copy the confidence interval calculator. We come back to the question. We paste it somewhere. We expand our cells where we need to. And now we just got to plug in our numbers. We want p hat. Well, boom, there's my proportion. I got it. 79%. Sample size. Boom, 375. Type 375. Now, how confident are we? We're going to be 99% confident. Okay, easy peasy. 99% confident. Now I'm done. Now I can make an interpretation. We see that our interval is 0.736 up to 0.844. So we are 99% confident the proportion of everybody in college who voted in 2012 is somewhere between 0.73 and 0.84. I have no idea what it is, but I know it's more than 70%. I know it's less than 90%. So I can definitely say a majority of college students voted because they're both over 50%. But I have no idea what that number is. And so somebody did a study and they found that 62% voted. Based on our confidence interval, can we say that number seems reasonable? And I hope the answer is no. Because we know, we are 99% sure that this process worked and gave us the right answer. That it's between 0.73 and 0.84, and this is only 0.62. So something's up with their results. Maybe their population at this college is, just different from the overall population. Maybe they did a bad study. All we know is that their number does not make sense with our results. And so we would say this is inconsistent. Something is up with that measurement. We don't know what it is. We don't know if these students are just really different from everybody else. We don't know if they messed up their study and they meant to say 92 or 82 or something like that. We have no idea. We just know we can't trust this number. It doesn't match what we are seeing. Because only 1% of the time does this approach not work. So we can be pretty confident that what we did is the right way of doing it. And so what we can essentially say is, hey, people, you need to redo your analysis or understand your people are just different, something to that effect. Yeah, so when the confidence interval is denied, what do you mean by that question?
Kind of like what you just said. I wanted to know what it meant when something wasn't working right. What do you say? And you said this is inconsistent.
Oh, yeah. So the result itself, we were talking about the 62 being inconsistent.
Yes.
We always talk about, when we say interpret the confidence interval, we're assuming, because this is highly probable, that it's right. And so the formal way of saying it is that we are 99% confident the true proportion of all college students, so you'd write that next, is between, and then you would just state your values, 0.736 and 0.844. And then, of course, we're talking about that answer down there, then you would say, therefore, we reject.
That's what I'm looking for right there.
Mm-hmm. Yep. We reject the claim of 62%. If it's a claim. If it's not a claim, this one's actually not a claim. It's just talking about their local population. We would say, therefore, their results of 62% is inconsistent with our population, which suggests that their population's a different population than your population. So it depends if it's a claim or just a comment. Because they might have done a survey of their local college only, which is what they're saying here. And so that local college's population is unique from the general college population. Like maybe they went to a place that just no one has time to vote. And so it's just not a consistent of your typical college student. All right, my friends, you might notice that this section is actually pretty straightforward. Once you build your formula, it's just a matter of copying and pasting and putting in the right numbers. And that will be the hardest part. And so I will post in the chat my own scribbles on here, and you can get the formulas that way. Or if you followed along in the video, you can also just learn how to build your own calculator yourself. I do really encourage you to practice building a calculator just in case, because some instructors are cruel and make you build them on the spot in the class, on a test, for example. Others allow you to bring in pre-built calculators. So you'll need to find out from your instructor if you can pre-build your calculator or if you have to do it on the fly. If you have to do it on the fly, then you definitely need to know how to do this coding yourself. In which case, go back and rewatch when I made them for you. But let's do the question. As always on the word problems, we're going to start at the very bottom because it tells you exactly what you need to do, usually. And there we don't really see a question, so we're going to go a little bit higher, and we can see it right here. Determine the minimum sample size. So that means that we're going to go and find the calculator that's about minimum sample size. We're going to copy it. We're going to jump into that question and paste it somewhere. Expand our brackets and find our three values. We need to find these three numbers. Once you have them, you're good to go. Well, our proportion is just the amount up here, right? The percentage group, which is 10%. Confidence level, you wish to be 95% confident. That's over here on the right. So 95%. And how much error are you willing to accept? We're willing to be within 4 points of error. So we're just going to write 4 percentage points because it says percentage, so be consistent. And there we go. If we do our survey, we better talk to 217 people. And if we do, we'll be within 4 percentage points. And that's it. So that just tells us how many people we have to survey. We have to survey 217 people in order to create a confidence interval that is exactly 4 percentage points up and 4 percentage points down from the center. So plus and minus 4% essentially. And that's all there is to proportions in terms of confidence intervals. Next week, I'll show you how to do confidence interval of means, and then into the ones that give people the most of a headache. It's called hypothesis testing. So just one thing to note for these guys, when we do them, after you make a confidence interval, it's just a matter of knowing, is the value between my measurements or is it not? If it's between them, we call it consistent or expected. If it's not between them, it's inconsistent or unexpected. Any language like that. For the sample size calculator, just remember we always round up unless they tell you in the question to round to the nearest whole. Kind of like the whole usual range thing. But that's it. That's as much as there really is to do with these things. Build your calculator. Once you have your calculator built, it's just a matter of copying and pasting into the question and filling in your numbers. And obviously, if you have a question that already calculates the error for you, then you don't need the calculator. Just add and subtract those values to get your answer. Go ahead, Melinda. What's your question? Is it about this stuff? Well, I am
sorry. I couldn't get my mic off. I'm sorry. With the two calculators that you did, the minimum sample size calculator has the rounded up sample size, and I have the formula for that. I have had errors with rounding in the past. So on the confidence interval calculator, none of that needs to be rounded. That can stay just the way that it is.
That is correct, because p hat is a relative frequency, so it's a continuous number.
Okay. And while we were doing this, I was trying to go through the book to see if I could find those formulas for it. I think my best bet is just to go back and listen to the recording and watch how you put those formulas in.
I encourage you, but you could find this, I think, on page 98. I just took a screenshot of part of the page because it's one of those long ones again, and I'm going to do like pieces of each one. So I'm doing all the whole page at once.
Oh, I was in the book. You're talking about in the lab manual.
Yes, sorry.
So, that's where I was. I'm sorry. I have that printed up.
Okay. Is there a second question?
That was it. Those were the two.
Oh, all right. Well, everybody have a great day. Florence, I see your message. I will send you the test reviews as soon as we're done here.